all, I want to welcome everybody this morning. Thank you for coming out to the early session. This is the annual Paul Pintrich Dissertation Award, which is given out to the top educational psychology dissertation of the year. Paul Pintrich, I think, affected a lot of us, directly or indirectly, in this room. And this award is recognition for all he did to the field and how he motivated current scholars today. I think the award is a recognition for hard work done, but Maggie, unfortunately, it's also a promise for future work. No pressure. We have distinguished recipients who are doing amazing work in the field today, so we recognize the work past and hopefully a promise for good work to come. Our recipient this year is Dr. Maggie Renken. She got her PhD from the University of Wyoming and is currently a professor at Georgia State University. Will you please welcome Dr. Renken?
Thank you, Martin, for that brief introduction, because I'm afraid I have too many slides, so it's good. The title of my talk is What are the Sources of Student Science Knowledge? A Consideration of Simulations in Epistemic Cognition. So this is really broad, and it's broad for a couple of reasons. It's broad because I wrote the title before I wrote the talk. I wanted to be sure that I had it all covered. It's also broad because I'm going to talk, of course, about my dissertation research, but I'm also going to set the context and talk about how I got there, and also talk a little bit about the work that I'm doing now and where I see this going in the future. So hopefully, I'll at least touch on each piece of this title, but we might not go as deep as we do broad today. So as I just mentioned, I'm going to start out by setting the context of my research, and then we'll talk about my dissertation project, which focused on computer simulations and clear observations in science experiments. And then hopefully we'll have time to really briefly touch on some work that I'm doing right now on children's thoughts about the sources of their science knowledge. So, begin by setting the context. And I want to start by talking about the educational context. And I'm assuming that most everyone in here probably has a good feel for the educational context, but I'm going to give you a little bit of background. First of all, I'm really focused on science education. And part of this is motivated by national competitiveness in STEM education. And so we see from reports like the TIMSS and PISA that the United States is not performing at the top. In fact, there are reports that we are performing around 8th. And so there's been a lot of attention on how we encourage our students to achieve better in science. We see this in things like, most recently, the Next Generation Science Standards that have just come out. And we see that there's an emphasis on, in particular, this notion of scientific practice skills, not just content knowledge. And one of the ways that we think that we can actually help children develop their practice knowledge as well as their content knowledge is to use something similar to inquiry-based science education. And so I'm always hesitant to talk about inquiry-based science education because it got a lot of attention. It's a pretty serious buzzword, and like anything that gets a lot of attention, it then was critiqued immediately and a lot. So inquiry-based education, I could spend a whole hour talking about what that is, but what I want to point out is the key is an emphasis on both content and practice knowledge. So when I talk about practice, I don't mean scientific reasoning skills, science experimentation skills. And the key here is that it often involves these long extended investigations that have some hands-on component for students. So there's been a large, the Inquiry Synthesis Project has actually looked at inquiry-based projects. And I think that the thing that stands out to me the most from the meta-analysis that these folks have done is that most of the studies, 45 to 61%, were coded as having marginal methodological rigor. So these are studies looking at how inquiry-based science education works, and most of these studies have not been very rigorous. Another interesting finding that I want to point out for an investigation of what's actually happening in inquiry-based science education is that when a group went back and looked at PISA data, the top performing science students reported the fewest hands-on investigations in their classroom. This is a real chicken and egg kind of issue, right? Maybe the top performing students don't need hands-on investigations to engage them, or maybe top performing students are performing because they're focused on something else other than the hands-on investigations. But I think that this is an important thing to think about. And as someone interested in science education, we've really got to figure out what it is about hands-on. So to set the research context now and where my research focuses, I am really particularly interested in early adolescence. And in case maybe you have forgotten, if you don't work with adolescents or you've forgotten what adolescence feels like, I've provided a reminder. These are adolescent polar bears. So adolescence is a time where these guys are going through some big changes. They're a little different. I think that makes them a lot of fun to study, especially in a scientific reasoning context. But when we talk about education, they're also transitioning into middle school or junior high, where they're in much more structured classrooms that are discipline-focused in science. Within science, I look at scientific reasoning, which I've already mentioned, and in particular today I'm going to talk about simple physics phenomena that I've examined with students. And I'm really interested in their inaccurate prior beliefs and how those affect the experiments that they run and the role of hands-on activities in altering those prior beliefs. So a little more background on prior belief bias. Prior belief bias is a reasoning bias that serves to protect or promote entrenched beliefs. So if you imagine an infant sitting in their high chair, dropping a spoon. Drop the spoon. If you've seen this happen, they drop the spoon, mom hands the spoon back, they drop the spoon, they hand the spoon back. They test it over and over. They then know that if I drop this spoon tomorrow, it's going to fall. And so if we think like a Piagetian, we understand that they're dropping this spoon and learning that gravity is going to make this spoon fall. It would be an incredibly chaotic world if we couldn't create these rules. Unfortunately, sometimes we create these rules and they're not accurate, and they may persist then from childhood to adulthood because it would be so chaotic if you couldn't create these rules. And so what happens is this often results in an inability to draw contradictory yet accurate conclusions. So if I create a prior belief that isn't accurate, it's very hard for me to change that. So the first study that I'm going to discuss today, I'm going to focus a little bit on a study that was conducted by Pintrich and colleagues because it was in motivation for my master's thesis work. And I'm going to talk a little bit about the research context and how I got to my dissertation question. And I'm hoping that that'll be useful for those of you who are in that phase, but I'm also hopeful that it will give some perspective into the kinds of questions that I was asking. So when I got to grad school at the University of Wyoming, I got there and I was eager to change the world, like everybody else who starts grad school. Like, I am going to change everything with my research. And I knew that I was going to figure out that hands-on, there was something really special about hands-on interaction in the science classroom, and I just had to figure out what it was. So I read this study by Pintrich and colleagues, and I'm going to slow down and discuss their methodology pretty carefully because I copy some of that and replicate some of that in the studies I talked about here. So what they had undergraduates do was they gave them two physics problems, one that was belief consistent about an incline, the incline of a ramp, and two balls traveling down the incline of that ramp. They also gave the participants a belief inconsistent problem in which they varied the mass of the balls that traveled down this ramp. So if you think about asking someone at a higher ramp, if I increase the incline, will the ball roll faster? People will say, yes, the ball will roll faster. If you ask people if a heavier ball will roll faster than a lighter ball down a ramp, they'll also say that the heavier ball will roll faster. So that's an inconsistent belief because it's not actually what should happen. So participants read the results of a fictitious experimenter, and then they were asked to draw a conclusion for themselves and also to draw a conclusion for the experimenter who ran this study. What they found was that for the belief inconsistent scenario, the participants, these college undergraduates, were more likely to draw correct conclusions for the fictitious experimenter for themselves. So when they read these experiments, they could actually draw the accurate conclusion when they were answering for someone else, but not for themselves. This suggests that they weren't actually revising their own personal theory. And we all, I think, know that our students are trained in taking tests and they're trained in giving us the answer that we want from our students. And so I think that that's what this suggests. What this doesn't address is the actual context for acquiring data or evidence. So where are students getting the information from? In this case, they were only reading an experiment. And it could be the case that these experiments in their minds were considered purely hypothetical. So of course I can give you the right answer after reading this. I know what this guy found, I know what he's going to answer, but I'm considering this a hypothetical experiment. So So this led to my master's thesis question, which was, is experimenting better than reading? And so I'm going to go through this pretty quickly, but there were two studies here. The first study was just with undergraduates, a mean age of 20, there were 76 of them, and we were interested in the effect of performing an experiment versus reading about an experiment on the ability to dispel their incorrect prior beliefs. In the second study, we added an adolescent population, so these were 7th and 8th graders, and we looked at developmental trends by having an adult population too, or college undergraduate population, and then also looked at the effects of structured versus unstructured experimentation, so the kinds of experiments they were conducting. So for study one, what I expected, remember the eager graduate student ready to prove that hands-on is great. For the belief in consistent problem, I expected that hands-on participants were going to draw more accurate conclusions for themselves. They were going to actually see this phenomenon happen, and they were then going to draw a correct conclusion. We used the same problem, a ramp, with the belief inconsistent and belief consistent problem. Belief consistent being changing the incline of the ramp, inconsistent being changing the mass. And we had a between subjects variable, and they were put into either the hands-on experimentation condition or a read-only condition. So the measures here, we had students give their predictions of what they thought were going to happen, and this was through a forced choice question. And it was the same forced choice question that they used to draw a conclusion. So for their conclusion, after they conducted the experiment, we asked them if the ball rolled faster, slower, or at the same speed when incline or mass was increased, depending on the problem. We then asked them a set of generalization questions. So they answered 3 real-world questions. So, for example, a question about a child traveling down a slide. And those scores ranged from 0, which meant they got none of those answers correct, to 3. We also looked at their experimentation adequacy. And to measure experimentation adequacy, we were interested in the number of trials that they ran and whether or not they used a control variable strategy. So you can see here that scores ranged from 0 to 2. And so 0 meant that they were not controlling variables, and they were running they were running 1 or fewer trials, so no trials or 1. So you might say, how does that experiment happen? If you want to stick around after the talk, I can show you videos of how that experiment happens. But so there are students who actually never set up a valid experiment to test the question of interest. To get a score of superior, they actually ran more than 1 trial, and they controlled variables in a way that they could actually answer the research question of interest. So our dependent variables here were their conclusion accuracy scores after conducting or reading about the experiment, as well as their generalization score. I'm not going to discuss generalization score very much today because, for the most part, it mimicked what we got with conclusion accuracy. We found that the problem type, that belief consistent versus the belief inconsistent problem, is actually a significant predictor of conclusion accuracy, as we would expect. They were right on the one that they knew all along, and they were wrong on the one they didn't know. Condition also was a significant predictor. This is good, right? I wanted hands-on to be better. Not the case. Read-only participants performed much better than hands-on participants. So you can see that read-only was almost at ceiling. When they read about the experiment, they answered, they drew the correct conclusion almost all the time. For the hands-on condition, they were about at chance. So they were not getting it after reading. This is not anything that's really revolutionary. A lot of people have done this before, so I'll remind you that this was my eager young master's thesis work. This is not revolutionary. That kids are not doing good experiments. And so the question that we asked after seeing that hands-on performance was so poor was whether or not there was an impact of the kind of experiments they were running. And there is an impact of the kind of experiments they were running, and we can see that to be correct within the hands-on condition, the adequate experimenters were correct 64% of the time versus the inadequate experimenters who were only correct about 44% of the time. Not a huge difference, but something going on there. Superior experimenters aren't included here because there weren't very many of them. It's hard to find people who run more than 1 trial and also control variables, and we'll look a little more at that in a few slides. So after seeing this effect effective experimentation adequacy, one of the questions was whether or not giving students instructions on how they could conduct their experiments. So kind of along the lines of David Clark's work with direct instruction. If we give this structured, hands-on condition, maybe these folks will get it. If we force them to run a good experiment, maybe they'll get it. And our second prediction here, because remember we were looking at developmental trends as well, is that adults would perform experiments that were better than adolescents. And so adults would be more accurate as well. So we've got a pretty complicated design here with the within subjects variable being that problem type. Everyone still answered belief consistent, belief inconsistent. And the between subjects variable being now these three conditions. We've added a structured hands-on, and we're calling that original hands-on a free hands-on condition, where they're given no instructions on how to conduct the experiment. Does anyone have any questions about the experiment? Should I breeze through that too quickly for how they actually react? Okay. So we also, between subjects variables, had, of course, an adolescent population and the young adult, the undergraduate population. Same measures, we got their predictions, conclusions, generalization questions, and we measured their experimentation adequacy again. Oh, so again, again, this is what happens. The read-only is almost at ceiling. And so this is the proportion of correct conclusions by treatment condition for just the belief inconsistent problem. We're not talking about the belief consistent problem now. What you see here is that the correct, this is proportions because I work in zeros and ones, right? So the proportion correct as you go up towards one, they're more correct. And so about almost 100% again for read-only. The read-only group was significantly different than structured hands-on and free hands-on, but the hands-on conditions didn't differ. So remember the whole decision to add this structured hands-on was we were going to force them to do good experiments, and then surely they were going to see the answer, they were going to give us the right answer, and that didn't actually happen. And I will point out, I don't think I have it up here anywhere, but I will point out that we did check to see if they did good experiments, and on paper, they did great experiments. The structured hands-on were doing everything that we thought they needed to do. They controlled variables and they ran multiple trials, they followed instructions, but their conclusion accuracy still did not change. So to break this down for you a little bit more, you can see that our predictions about adolescents and adults are correct as far as the free and structured hands-on conditions go. They perform a little better. But you can see that they're coming into this with equal proportions. If you look at prediction, 22 versus 28% in the adolescent and adult populations are coming in with the inaccurate prior belief. And so it's not that the adults have figured it out at this point. They still haven't figured it out. And they were just doing a little better after conducting the experiment. And I'm drawing circles to direct your attention. Okay. All right, so again, eager grad student, at this point panicking because nothing is turning out the way I want it to turn out. Right? So I've set out to say hands-on is great, and now I keep doing these experiments and hands-on is not great. And so I'm going into committee meetings and my committee is saying things like, so wait a minute, you're studying prior belief bias with kids doing experiments and not believing their data, and you're having a hard time accepting the fact that read-only is better. And so I then said, okay, wait, but maybe these folks who did get it in the hands-on condition, maybe if we go back 12 weeks later, those folks are going to get it. They're going to remember it better than the kids who read about it. Maybe the ones who read and got it correct just know how to take a test. They know how to give us the answer that we want. So we went back 12 weeks later. I went back 12 weeks later and had a group of adolescents answer the time one conclusion question. Because this was post hoc, again, this was a panicked moment of trying to figure out what's happening. Because this was post hoc, we didn't have a way to know if they were in the free or structured hands-on condition, so we had students self-report if they read about the experiment or conducted the experiment. It was only the case that 2 students 12 weeks later couldn't remember if they actually ran an experiment with the ramp or read something. So for the most part, they remembered that they were hands-on or read-only. So in comparing these 2 groups, here we go. There is a significant interaction between the hands-on and the read-only group. So I'll walk you through this graph, because I feel like at conventions I always end up like, wait, I need more time with the graph. So I'll walk you through and show you what's happening here. So again, proportion of correct conclusions over time. You'll probably notice that this looks good for hands-on because we're above 50%. Remember that this is both problems, both the belief consistent and belief inconsistent problems. So this is overall accuracy. So you can see that hands-on actually maintains that knowledge relatively well. And these means are, I believe, 0.56 and 0.57, or the proportions of 0.56 and 0.57. But you can see with the read-only that they're actually losing that knowledge over time, which we expect with learning, right? That over time we would see a decline. But with the hands-on students, we aren't seeing that. So this is somewhat hopeful, right? That there's something. But now the question is, how do we get more of the kids to see it, to see what, to not believe their own prior belief, but to believe what they're actually seeing? How do we get them to see that? And so that's, I'll show you some conclusions, and then we'll talk about how that's led into my dissertation work. So the main conclusions from here are that adults do draw more accurate belief and consistent conclusions than adolescents, and that there's no difference in the structured versus hands-on condition. I think this is important because it looked like they were doing so well. So we can have ideas about what experimentation should look like, but if we're not really sure what's going on inside the child's mind as they're doing this experiment, we have to be pretty careful about how we're gauging their interaction with some scientific phenomenon in the form of an experiment. Importantly, reading about the experiment led to more accurate conclusions than performing the experiment again, and this was the case for both adults and adolescents, and after a 3-month delay. The read-only are still performing better. But it's important to keep in mind that hands-on results led to better temporal transfer. So over time, these students in the hands-on condition actually maintained that knowledge better than the read-only condition. And I want to point out, too, for this first conclusion, that the adults drawing more accurate, because remember, these are college undergraduates, and we know that when we look at physics research, these students are still having a hard time with prior belief bias. So I do want to point out that I think part of it's obvious from the data that we collected that they're conducting more adequate experiments, and this might be what's driving this effect. They've gotten a little bit better at controlling variables and learning more skills. So this is when I stopped and thought, how can we figure out how to get kids to actually see what's going on? So if you imagine having this mass problem, the idea that something heavier is going to fall faster, if you imagine how quickly that happens, it happens in an instant. So if I were to stand in front of you and I forgot to pack my steel and plastic ball, but if I were to stand in front of you and drop those two, the instant that they hit the ground is so fast that it's very easy to rely on your prior beliefs because you don't really get to see what happens in that quick moment. And so one of the suggestions is that computer simulations are beneficial for multiple reasons. First of all, they can help us slow down the instant of impact, or the moment that we're interested in seeing. And if we do that with a computer simulation, perhaps students then will be able to alter their inaccurate prior beliefs. The other part is that we can eliminate a lot of these extraneous variables that get in the way. We can allow students to set up these good experiments. And so this next step, when I began putting together my dissertation project, was to see if this was actually the case, that computer simulations were better than these hands-on experiments at allowing students to change or alter their prior beliefs. And notice that I keep calling these prior beliefs. I'm very careful to not refer to them as misconceptions because it's the kind of experimental work that I'm doing. I'm going in very briefly, and so we can't talk about this in terms of large, broad conceptual change. There's also a suggestion that observation clarity may be something that's important for students to alter their inaccurate beliefs. And so we wanted to look at that as a factor on its own. And so one of the things that I manipulated was the slow motion versus real-time replay of their results. And so everyone who conducted an experiment was then shown their experiment on a video screen, either in real time or in slow motion. And so they had two different kinds of interaction environments. They either conducted the experiment hands-on, or they conducted the experiment on a computer. And so when I say that the replay, they watched a video, they either watched a screenshot played back, or they watched a video of them immediately after conducting the experiment with the hands-on apparatus. So very similar design, except this time we were looking at pendulums instead of ramps. And part of the motivation for that was we're still talking about the same Newtonian physics, but the computer simulations that were available were much tidier for pendulums, for exploring pendulums. And so it was easy for us to set up a computer simulation and a hands-on apparatus that were very similar. So we expected that slow motion observation then was going to lead to more accurate conclusions based on the prior work that they couldn't actually see what was happening. And so maybe if we slow it down, they're going to be able to make more accurate, draw more accurate conclusions. I also still fought for this prediction that physical engagement was going to lead to more accurate conclusions. So I'm still eager to show that hands-on has some benefit, and especially when pitted against computer simulations. And part of the argument that I made for this, based on prior literature, is that adolescents, especially undergraduates, have been shown to blame errors on computer fault. So this notion that they understand that computers may not know all, and they can make mistakes. And so I still clung to this idea that there's something about seeing it for yourself and this physical interaction that's going to be beneficial. This was a mixed design as well. This time, the between subjects variables were both the observation clarity and the interaction environment. So students were either in a physical real time, a physical slow motion, computer real time, or computer slow motion conditions. So 4 different conditions they were put into, but we maintained this within subjects variable of the problem type, the belief consistent versus belief inconsistent problem. 144, again, early adolescents, so these were 12-year-olds that I ran experiments with individually and videoed and played back. So it was a lot of time for the dissertation. So the measures, again, were similar to what I've already shared with you. This time, though, added confidence in prediction, and I'm not going to talk about that here, but if you would like to look at the paper, I have a link on my own website, but you can also find the paper. And then we talk a little bit about this role of the confidence in their prediction. So I'm going to show you guys some videos of what this actually looks like. So this first video is an example of a kid who conducts an adequate experiment. He's controlling variables, and he is in real time. And so you can see he has a plastic ball and a steel ball, and this is actually the video that they saw the replay. So he does one trial and he's good. Now he's changed the string length, and this is the belief consistent problem. Everyone predicts that that shorter string length is going to go faster back and forth. But they typically make an inaccurate prediction about that first problem with the heavier ball and a lighter ball, expecting that they won't come back at the same time. So I'll show you the slow motion, and we won't suffer through the whole slow motion, but I'll show you what this looks like. So they watched the replay in slow motion, and this is again an adequate experiment. And so he let it swing for a while, and then this is for the belief consistent problem. Okay, I'm going to show you an example of a student who does not control variables. This is fun. So she's controlling variables the first time. She's testing the impact of mass. And now she's testing string length. And notice she has, I don't know if you guys might be able to see that. So there's a plastic ball and a steel ball. So she is changing string length and mass. She lets it go a couple times and she writes down her answer. She moves on. She's got it. She has the answer to the string length problem. And so that was actually pretty common that students were doing that and not controlling variables. The computer simulation, I'll show you a screenshot. The actual computer simulations were, it gets a little choppy because of the screenshot. But you can see that they had the option to move length and mass for both the first and second pendulum. This is a FET simulation from UC Boulder. So for the slow motion replay, they clicked the 1/4 time button that you can see here to replay the exact same experiment that they had trial that they had just run. So they also saw every trial in slow motion. These were pretty obvious. So when you have two with the same string length and you hit play, they move perfectly together. No question, they're moving at the same time. And I share that with you because we're about to see what happens with the results, and it's surprising again. So for this work, I used generalized estimating equations. So it's an alternative to logistic regression because we have a within subjects and a between subjects variable. And so to take care of that repeated measure, which was the problem type, we used GE, looking at conclusion accuracy, which was this binary variable. So the model that I first ran included problem types, so the belief inconsistent versus belief consistent problem, the observation clarity, whether or not they saw it in slow motion or real time, excuse me, the interaction environment being the physical versus computer simulation, the hands-on versus computer, and then their experimentation adequacy we included again. So the significant predictors here, problem type, as we expect always, and experimentation adequacy. The two conditions that I was interested in and had made predictions about were not significant predictors of their performance. Everyone, I know it's 8 o'clock and I don't know why, but this should be a little more shocking. They watched it in slow motion on a computer, and this still was not predicting with the conclusion accuracy. And so maybe what we can say to that is, well, so what you're comparing is hands-on and computer simulations, real-time slow motion. Maybe everybody's just doing great. They're not all just doing great. So I've drawn a line here at chance, at 50% correct, and condition is across the bottom here. So you've got the physical real-time, the physical slow motion, computer real-time and computer slow motion, and belief inconsistent, again, is what we're really interested in. When we look at the belief inconsistent problem, no one is performing above 50% accuracy rate. They're not altering their prior belief. And we're not seeing a really big difference with this slow motion component. We're not seeing really no significant difference. Now does everybody have time to realize that that's kind of good. So again, remember, eager grad student. I have to go back again to my committee and say, that my conditions are not, that, slow motion, computer versus physical, not making a difference. The best fit model that we ran then with the interaction term between the interaction term with the two significant predictors, problem type and experimentation adequacy, all three were significant predictors. And so we'll look now at what this interaction term actually shows us. And I think that the important thing to notice here, so on the y-axis, again, we've got percentage correct now. I'm not sure why I switched from proportion to percentage, but we've got percentage correct here, and then we've got their experimentation adequacy, inadequate, adequate, superior, and the two problem types. Belief consistent is that darker color, belief inconsistent is the lighter color. And what we see here is that the inadequate experiment for the belief inconsistent problem, they're really not getting anything out of that inadequate experiment, obviously. What I think is also very interesting is that there's no difference between the superior experimenters between the two problems. So, let's see if we're going to have time. Okay, so this is time 2. So we went back again 12 weeks later, and now included time as a predictor in this GE model. And so is there an impact of a 12-week delay in their conclusion accuracy? And in fact, time is a significant predictor. As we would expect, problem type and experimentation adequacy both remained significant predictors over time, so experimentation adequacy still mattered, and the time by problem type interaction was significant as well. So of course, we can think about that. If you know the answer, you do an experiment for the belief consistent problem, you know it going into it, you do the experiment, you're going to know it afterwards, and you're going to know it down the road. If you do a belief inconsistent experiment, you didn't know it to begin with, you're probably not going to know it later. Now I'm going to share what I think is the most interesting thing from this project. So with the generalization score outcome measure, remember these were real-world problems that we gave them 3 questions for each concept. And we found that problem type was still a significant predictor, but there was also a significant 3-way interaction between the problem type, experimentation adequacy, and the time 1 versus time 2. Does anybody know what a 3-way interaction means? While you're sitting here at 8 o'clock in the morning, imagine. I won't make you imagine. I'll show you. So at the top here, we've got the belief consistent problems clustered, and they're the inadequate, adequate, and superior experimenters. And so generalization scores, remember, range from 0 to 3, 0 being none correct, 3 being all correct. And as we expect, belief consistent, they're performing better on those problems, so that's why they're hanging out at the top in that cluster. Belief inconsistent, again, they're not performing as well in that, and so they're clustering down at the bottom. We see the effect of time that we expect with learning from time 1 to time 2. There's a decline across all of these. The most interesting thing that I want to point out here, and we also see that inadequate experimenters are are drawing fewer, or answering correctly less often than the adequate and superior experimenters. Has anybody had a moment to realize what this means, though? These are the students who were inadequate experimenters on the belief consistent problem, and this is their performance from time 1 to time 2. So this is a problem that everyone coming in knew the answer to, and the ones who conducted a poor experiment 12 weeks later had the greatest decline in their knowledge, in the accurate knowledge. They were answering this question inaccurately, these questions, incorrectly. So what actually happened when I went into this project to show that there's something special about hands-on, we can help take inaccurate prior beliefs and help these students get the accurate prior belief. And lo and behold, I managed to take a small group of 7th graders and completely destroy the one thing they did know to begin with. Over time, they had lost that knowledge when they performed an inadequate experiment. So I think this is the most interesting finding in this project. Let's see how much time. I'll go ahead and show you a little bit more of the data and kind of break it up in some different ways. So experimentation adequacy across interaction environment was the next place for me to look. What's actually happening when kids are conducting experiments on a computer and hands-on. And what we see here is that the inadequate experiment was much more likely for the computer-based experiment. So when they were playing on a computer, their experiments were not as neat and tidy. They were also much more likely to perform adequate experiments than for the physical experiment. In trying to figure out what that meant, I also went back and looked at the data and looked at those 2 components that we were combining to come up with their experimentation adequacy score, which is the number of trials run and the control of variable strategy. And breaking those down, we looked at what kids were doing with the hands-on apparatus and what they were doing on the computer in terms of controlling variables and running trials. Well, in the physical experiment, they were doing a much better job of controlling variables. So 91% of the kids doing a hands-on experiment were controlling variables versus only 60% of the kids in the computer simulation controlling variables. This is important to know because a lot of the simulations that are used are not, they're using kind of this inquiry approach, which means that they're allowing kids to, or a discovery approach, they're allowing kids to discover the concepts on their own. And so they have the freedom to not control variables. With the computer simulation, there were a greater mean number of trials run. So in interpreting this data, one of the things that we assumed was happening was that students and computers were more likely to play a little bit more. So they're running more trials and they're not controlling variables, so there's a little more play happening. So I'll walk through these conclusions, and then we do have a little bit of time for me to talk about where this is going now and how I think this is how this is kind of set up where my research is headed. So the first conclusion here is that observation clarity and the interaction environment did not affect the student's conclusion accuracy. So contrary to my expectations, again, didn't find the effect that we were expecting. Prior belief bias accuracy. This could also be thought of in terms of the problem type. And experimentation adequacy were actually the key predictors of conclusion accuracy. I think as far as implications for educators and for education researchers, I think it's important that we think about going into it, and this isn't novel either, I think most of us know this, but we need to know what our students' concepts are before they come into the classroom so that we then know how they're going to interact with the data. Computer simulations also result in fewer adequate experiments. And I think that this is very important when we start to think about the design of computer simulations and how we're having students interact with phenomena online. And fewer adequate experiments here in particular meant that they were running more trials, but they were less likely to control variables. The big point here, I think the most surprising finding and what I think is most interesting and most important for us to be aware of, especially when giving students, sending them off with their laptops and having them work on simulations, was that poor experiments not only hinder the alteration of inaccurate prior beliefs, so they don't just stop us from changing our mind and having the right answer, they may actually allow the alteration of accurate ones. So we actually saw that these students performing those inadequate experiments are actually losing the content knowledge that they have. So this has really pushed me in the direction of thinking more about children's thoughts on the sources of their science knowledge. So do they actually value hands-on experiments? Do they value computer simulations? Do they value what their teacher is telling them? What are their actual thoughts about the sources of knowledge? And I have just a few slides here, and I'll go through them very quickly. I'm very interested in talking to anyone else who's doing research in this area about this more. But I just wanted to share it briefly. I'm hoping I can show you a video of a student who really demonstrates this prior belief bias in a beautiful way as soon as I finish talking about this too. So when we think about epistemic cognition, and there were some great talks on epistemic cognition yesterday, one distinct component of it is the sources and justification of knowledge. And I think that this is particularly relevant to thinking about how kids are interacting with computer simulations. And I think especially adolescents who may be rather skeptical of some sources of knowledge, especially as they move into this more multiplist phase of thinking, they may become more skeptical and require this kind of physical hands-on interaction. So to really look more closely at developmental shifts and how kids are evaluating actual sources of science knowledge, we've investigated recently a few research questions related to how kids evaluate explanations across grade level and how the observability of the topic that someone's explaining actually affects students' evaluations. And so I'll give a little more information about what that means. So we gave kindergarten through 8th graders a task where they were told that a teacher, Ms. Smith, has asked her students how they know plants grow, how they know the earth moves, and how they know the dinosaurs once walked on the earth. And these three scenarios we're thinking of as changing in terms of their observability. And so this first scenario, plants growing, it's very observable. I can see that happen in my front yard. The earth moving is more difficult to observe, so this is a scientific phenomenon that I may not get to see. As far as the final one goes, I can't actually see dinosaurs walking on the earth, so this is impossible for me to observe. And so we gave students two explanations from two fictitious students about how they know these phenomena are true. And so you can see an example here that for the plants growing, the first child says that she's seen flowers in her front yard grow. The second child says that her teacher has read a book about how flowers grow. So the way that we paired these were that one was from this physical experience, actually interacting with the evidence, versus this more indirect evidence that they've received from some kind of authority figure. We don't have to dig into this, but I wanted to just show you that this was the outcome that we're looking for. And so we're having students make these decisions and then fitting them into a pathway. And so we first ask them, is one of these explanations better than the other? If the student says yes, we say which one is better, and then they decide whether the indirect or direct source of knowledge is the one that they prefer, and we put them into one of those two pathways. If they say no, one of these answers is not better than the other, we then ask, is there any way to make the answers better? And they can either answer yes or no. And if they say no, we assume that they're accepting, like a multiplist thinker would, that there can be multiple sources, multiple explanations, and they can be equally good. If they say yes, I can make these answers better, we're putting them into what we're calling an evaluativist pathway, because they have the understanding that I can now think about these sources of evidence, these explanations, and I can combine them in a way, or I can change them in some way to make one better than the other, or to make them both stronger. So I'm going to share with you quickly a couple of the findings from this project. So these are kindergarten through 8th graders. We've collected data of 487 of them. And our prediction here was that across development, students would become more mature in their epistemic cognition and their thinking about sources of science knowledge, and that maturity would be reflected in these more multiplist or evaluativist pathways. And what we found is, in fact, that's what's happening. And so kindergartners, you can see, are very high on the direct and indirect choices, so they're making a decision with yes, one is smarter than the other. And we also see that with time, the multiplist and evaluativist pathways are also increasing as we get to the 8th grade. This is across the observability topics, so I'll also show you what we're finding here, and there was a difference in the 3 scenarios. And so for an observable topic, across development, students felt like a direct piece of evidence, so seeing the flowers grow in the front yard, is actually fine. That's something that is a good explanation, and I'm comfortable with accepting that as a good explanation. But we see that that changes as we go to these impossible to observe or difficult to observe phenomena. So that's just a teaser for where I'm headed now to think about how kids are viewing sources of knowledge, and that maybe there is some component with regard to epistemic cognition when we're giving these kids computer simulations and hands-on experiments to work with. I want to say thank you to lots of people who have helped with all of the projects that I talked about today. Particularly the University of Wyoming Science Posse and John Roth, who ran that, because it was a lot of fun to go out into schools and meet teachers and teach kids how cool science is. And I got to do that in grad school. And Marina Nunez, who was my advisor at the University of Wyoming. So I can start answering questions, but I'm going to look up the video, okay, and show you guys if I can figure out how to make this stuff. Okay, so this is a student that I always share this. Anecdote about the data that I collected. This student came into the room, and I asked him for his predictions, and he said the plastic ball is going to go way faster than the steel ball. He was really excited about getting to do an experiment, and he knew the answer. And he said the plastic ball is going to go a lot faster. And so he runs his experiment, and he's in the slow motion condition. And I'm going to let this go so that we can watch. He runs it. We'll get up to where he drops it. So he runs it, and as soon as the balls leave his hand, he goes, oh, whoa, 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 I know what I did. I know what I did. I need to do it again. I know what I did. And so I say, we need to watch the slow motion replay, and then you can conduct another trial. So he watches the replay the whole time going, I know what I did. I'm ready to do another trial. And so he starts this other one. I want you to watch carefully what he does. So in case you missed that, I just love this. And so this is slow motion, and you get to see what he did really, and I think it's a good point for us as researchers too. These little things that we do without even realizing that he had dropped that ball first. And immediately went, yeah, that's right. That's right. He didn't even look at the slow motion replay. He never picked up on the fact that he let go of the plastic ball faster. And I think that this is also a good point with regard to their experimentation adequacy. So one of the things that we did was look at number of trials and think that number of trials actually meant they were running better experiments. But what we found, in a slide that I didn't include for this, is that when they're looking at the belief inconsistent problem, they're running a lot more trials. And this fits with kind of motivated skepticism, right? This notion that if you really want to test something and find your belief, you just keep testing to find what you believe. They weren't running more trials for the belief inconsistent problem because they weren't doing it so they could find the right answer. They were doing it